Okay, so we were doing the rate of a reaction, and we will be starting the catalyst, how it's the factor that how the catalyst affect the rate of reaction. So basically we know that these are the substances which basically speeds up the reaction. So how catalysts will do it? The most important thing that catalyst does uh, catalyst itself remains unchanged at the end of the reaction. So what catalysts do? Catalyst provides an alternative route. And actually, what is the alternative route? It is the one which have the lower activation energy. And it route means mechanism that how the reaction occur. So now the reaction occur in a different way, which needs relatively less amount of energy to for the reactants to turn into product. And if the energy is lesser, so there will be more number of particles which can colliding effectively. Is this point is understandable to all of you?
Yes, sir.
Yes, yes.
Okay. So this alternative route has lower activation energy, hence more proportion of particles has energy equals to or activation or greater than activation energy. And here we are talking about the new activation energy, which is lower, okay? Is this clear to all of you?
Yes, sir.
Now what will happen as a result? More frequent successful collisions hence rate of reaction will increase. Is this clear to all of you?
Yes, sir.
Yes.
Yes, Hamza, Kubra, and Yusuf.
Yes, sir.
Okay. Okay, now after catalyst, we have a next, that is temperature. So either temperature would be the lower or the temperature, there will be a higher temperature. So we are going to discuss both the conditions and how it will affect the rate. So at lower temperature, particles has lower kinetic energy. So it means that if the particles have lower kinetic energy, so it means there are, out of the total particles, there are less number of particles who have energy equals to or lesser than activation energy. So that's why we will say, so the proportion of particles, for example, there are 100 molecules, and out of those 100 molecules, only 20 molecules have an energy which is equal to or greater than activation energy. So the proportion of particles having energy equals to or greater than activation energy is lower. So less frequent successful collisions occur. Hence, rate of reaction decreases. Is this clear to all of you?
Yes, sir. Yes, sir.
Yes,
Yes,
sir.
sir.
Okay. Now, at higher temperature, what will happen to particles? They gain energy. So particles has higher kinetic energy, and the proportion of particles, it means, for example, as I have told you, initially at lower temperature, there are only 20 molecules who have out of the 100 have energy equals to or greater than activation energy. So probably this time when the temperature is high, now there are, let's suppose out of 100, 45 molecules have the energy equals to or greater than kinetic energy. So see, the proportion is increased. Is this understandable?
Yes,
Yes,
sir.
sir.
Yes.
So the proportion of particles having energy equals to or greater than activation energy is greater, leads to more frequent successful collisions, hence rate of reaction increases. Okay. Yes, is this clear to all of you?
Yes, sir. Yes, sir.
Okay.
Yes, sir.
Now, beside this, the next thing that we have to discuss in this chapter is Boltzmann distribution. It is related to the distribution of the particles at any specific temperature. So for any sample of a reactants or any sample of a substance, at given temperature. Okay, you all know that all the particles which are present in any sample does not have equal energy, right? So out of those, all the number of particles, there are only few particles who have relatively higher energy, right? Only there are only few particles which have very high energy. In the same way, there are few particles who have relatively we can say very low amount of energy, and the rest of the particles, so the most of the particles have the energy in between these two limits. Is this understandable?
Yes, sir.
Yes, sir.
Okay. So basically, Boltzmann distribution is the graphical representation of this energy distribution that we have discussed. So the graphical representation of the energy distribution among the particles at given temperature is called Boltzmann distribution. So you have to know how to draw the Boltzmann distribution at different temperatures and its labeling as well. So on x-axis, we keep molecular energy, and on y-axis, here we keep number of molecules. So at this point, will the energy higher or lower? Yes. At this point, will the energy, is the energy higher or lower?
Higher.
Higher.
sir.
And here the energy is lower, right?
Yes, sir.
Okay. What about this point? At this point, the energy would be higher or lower?
Lower.
Lower.
Lower. Okay. So as we have discussed, so the graph would be like this. See, when the energy is higher, at that higher energy, there would be very low number of molecules. Okay, it's not. It's like this. So if you see at higher energy, there are very less number of molecules, and at lower energy, there are also very less number of molecules, and there are the maximum number of molecules are at the energy which is in between. That's what we call most probable energy. Is this clear to all of you?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So the area under the curve represents the total number of molecules present in a sample. And on energy axis, I'm putting this line. It means that this is activation energy. So what does this activation energy means? Yes, can anyone tell me? It means that whatever the number of particles which are at this energy and above this energy all the molecules have energy to collide successfully. And if we look at this whole shaded region, this shaded area represents the proportion. See, this is the only proportion out of this whole proportion which can collide successfully. Is this understandable to all of you?
Yes, sir.
Yes, sir.
This shaded area represents the proportion of molecules from the whole sample which possess enough energy to form product on collisions. Okay. So is this clear to all of you?
Yes, sir.
Okay.
Yes, sir.
Now there is a rule which states that for every 10 degrees Celsius raise in temperature the rate of reaction actually gets double, approximately, not exactly. Rate of reaction approximately doubles. Is this clear to all of you?
Yes, sir.
Yes, sir.
Okay. If anyone of you have any confusion in this, sometimes examiner give this in MCQs paper 1 as well. You have to know that at this point there are the most number of particles, right? So this energy over here on x-axis is the most probable energy of the molecules. Is this clear?
Yes.
Yes.
And out of the whole area, these are the whole number of molecules. Out of these, only the number of molecules which are present in this area will do the successful collisions and form product, and rest of the molecules do not collide successfully. Is this clear?
Yes, sir.
Okay. Now you have to know that if the temperature is raised, how the shape of this graph will change. Okay. Now, let me do one. Now here we are going to see the shape of the graph at higher temperature. So this is the temperature T, and we are going to observe the graph at a higher temperature, 10 degrees Celsius more higher than this. So as we have discussed earlier, as the temperature raises 10 degree, what will happen to the rate?
Double.
The rate doubles.
It double.
Yeah, it means if the rate doubles, then this proportion of the molecules will actually almost get doubles. So there will be the successful collisions will be the double, and the rate of the reaction will be double. Is this understandable?
Yes,
Yes, sir.
Okay.
Yes, sir.
So when we increase the temperature, what will happen? Particles gain energy, right? So when the particles gain energy, what will happen to this curve? Isn't it? It moves towards the right, because at right there will be the more energy. So as it moves to the right, from here it raises, and from here and here it goes down. Is this understandable?
Yes, sir.
yes, sir.
So it will be drawn like this. Isn't it like this? So now see, the total number of molecules remains same, but the proportion of the molecules which were doing the successful collision now gets double. Initially, the green shaded area will be doing the successful collisions and forming the product. Now this green plus blue area is undergoing these number of molecules from the whole undergoing successful collision and form product. Is this clear to all of you?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So this whole region. So now we have greater proportion of molecules have energy equals to or greater than activation energy causes increase in rate. Is this understandable to all of you?
Yes, sir.
Okay. Now we are going to see how what will be the shape of the curve when the temperature gets lowered. So here, this is the curve at temperature T. And now we are going to see at another temperature, which is 10 degrees lesser. So if it's 10 degrees lesser, then it means the rate would be halved. And if the rate would be halved, then these proportion of the molecules actually get halved, right? Sorry. So as the energy of the particles got slower, so the shape will be like this. At lower energy, now we have a more number of particles, and that's why the height of the curve increases from here, and from all these places, the height of the curve decreases. Yes, is this clear to all of you? Now,
Yes.
only this proportion of the molecules basically undergoing successful collisions. Okay. So we can write over here a lesser proportion of molecules have energy equals to or greater than activation energy causes decrease in rate of reaction. Is this understandable to all of you?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Ahmad, Kubra, and Yusuf.
Yes.
Okay. Now, after this, the next subtopic, the last one that we have is called catalysis. So what is catalysis? Can anyone know? Yes, can anyone know what does catalysis means? Basically, catalysis are those chemical reaction in which catalyst is used. So if we are performing a reaction without catalysis, then that's we cannot say it's a catalysis. But when we do the same reaction by adding a catalyst in it, then it is catalysis. Is this understandable?
Yes, sir.
Yes, sir.
Okay. So you have to understand the how it will affect the Boltzmann distribution as well. So what do you think how it will affect the shape of the Boltzmann distribution curve? Any idea?
Sir, the energy will lower, the activation
So what
energy will
happens to
lower,
the
so
shape? What happens to the
so
shape?
it will move to the right.
What will move to the right?
Uh, the the curve.
At right, isn't it? There will be a higher energy, but see, it does not affect the shape. Only see what will happen right now. This is the activation energy, right? So when we add the catalyst, this energy changes and now it will come over here. So see now, due to this, there will be the more proportion of the particles. So it gets lower, but shape doesn't change, okay?
Right, sir.
So catalyst does not affect the shape of the curve of Boltzmann distribution. So see here we have a Boltzmann distribution curve. What happens only when we have when the catalyst is added? Now this is the new activation energy due to the catalyst. So now this proportion, the proportion that is present in the shaded region, now this proportion of the molecules will turn into product. Is this clear?
Yes, sir.
If
Yes,
any
sir.
of you have any confusion, please ask. Okay. So if you see, before catalyst is added, this is the proportion of the molecules which were doing effective collision without catalyst, right? And when catalyst has been added, so this is the proportion of the molecules which were now effectively colliding in the with the catalyst. So see, the proportion of the particles increased. Is this clear?
Yes, sir.
Yes, sir.
Okay. So there are two types of catalysis. One is called homogeneous catalysis, so it's a reaction in which both catalyst and reactants are in same phase. And phase means that they are in same state. For example, if the reactants are liquid, then catalyst must be liquid or aqueous. If the reactants are solid, so the catalyst must be solid. Is this understandable?
Yes, sir.
Okay.
Yes, sir.
Yes, sir.
Example, both reactants and catalyst are either aqueous or gaseous. If the catalyst If the reactant is gaseous, then the catalyst must be gaseous, then it is heterogeneous catalysis. Now have a look at the equation for such kind of a reaction that usually occur in atmosphere where sulfur dioxide gas reacts with oxygen gas. We have discussed this reaction. We will discuss it in nitrogen and sulfur as well. Forms sulfur trioxide gas. If we balance it, we will put a half over here. And for this reaction, the catalyst that is used is NO2, which is also a gas. So see, the reactants are gaseous and the catalyst is gaseous. So hence it's uh, homogeneous catalysis. Is this clear to all of you?
Yes, sir.
Yes.
Okay.
Yes, sir.
Okay. Now, an important thing about homogeneous catalysis that they do take part in the reaction, but they form some intermediate in between the reaction, and as the product forms, they get restored. So homogeneous catalyst reacts and form some intermediate, but as the product is formed, that intermediate restored back into the initial form of catalyst. So that's why at the end, we get the catalyst only. Is this clear to all of you?
Yes, sir.
Yes, sir.
Okay. Then we have heterogeneous catalysis. So it is a reaction in which both catalyst and reactant are in different phase. And when we say phase, it means state. And here we have examples for this. For example, the Haber process, where we use nitrogen gas. Just give me a minute, please. Okay. So nitrogen and hydrogen gas reacts, and as a result, they form ammonia gas. And for this reaction, the catalyst we use is iron, which is solid. So see, the gas reactants are in the gaseous state and the catalyst is solid. So this is a heterogeneous catalysis. Another example, it's for hydrogen peroxide, and it's in aqueous state. It decomposes to gives water and oxygen gas. To balance the equation, I have to put a half over here. And see, the reactant is aqueous. For this, we use manganese 4 oxide MnO2, which is a solid. So the reactant and the catalyst have different states, are in different phase. So it's a heterogeneous catalysis. Is this clear?
Yes, sir.
Okay.
Yes, sir.
Here, another important point. As we have seen that here the catalysts take part in the reaction and form intermediate, right? So when we talk about heterogeneous catalysts, so heterogeneous catalyst does not take part in the reaction, does not react reactant molecules react on the surface of solid catalyst. Is this clear to all of you?
Yes, sir.
Yes, sir.
Yes.
Yes, if anyone of you has any confusion till here, please ask. Yes, Ahmed, is this clear? Yes, Hamza, Kubra, Yusuf, Amna, and Ashal.
Yes,
Yes.
it's clear.
Yes, sir. It's clear.
कैटलिस्ट जो होता है उसकी स्टेट से सॉलिड भी हो सकती है
Sorry, no. We were talking about solid most of the cases when there is a heterogeneous catalysis. Usually the most of the time or maximum time the catalyst is solid, okay?
ओके
Okay. Now the last thing I need to discuss, and then from the next class we will be moving towards inorganic chemistry. Here we go. See, this is the course of the reaction, and they have shown that how the reaction is taking place. And if you look at, this is the concentration, and here we have a time. So as the time passes, the concentration will decrease. So what it indicates, whether it's a reactant or a product. So it indicates that it's a reactant. Is this clear? Yes, is this clear? As we have seen the graph, as the time passes, as the reaction proceeds, the amount or the concentration is decreasing. It means that it is the concentration of the reactant.
Yes, sir. It's clear.
Okay. Now,
Yes, sir.
for example, if you need to calculate the average rate, what you will do? See the initial amount, which is 1.5, and when the reaction has stopped, the amount which is 0.3. And how much time it takes? 40 minutes, right? So the expression or the formula for the rate to calculate is change in amount per unit time, right? So we got the change in amount, and in which time 40 minutes we multiplied it by 60 to convert into seconds. And as a result, we will get the average rate of this reaction, which means that 5 mole exponent minus 4 moles per dm cube is being turning into product per unit second. Is this understandable to all of you?
Yes, sir.
Okay,
Yes,
if
sir.
I have to calculate the rate of reaction, yes, for this time duration. So what I will do, I will look for the change for this time duration. So starting from 1.5, it is ending at 1. So I got the change in amount. In how much time this amount is changed? In 10 minutes. So I will keep it in the denominator and then solve it. I will get the rate. Is this clear?
Yes, sir.
Yes, sir.
Okay. Now for 20 to 30 minutes, it means now we need to find the rate from this to this span. So see, if we see, it's like this. So this is the change. We got that change in the numerator and the time in which it is this change took place, that time in the denominator, and then solve it, we will get the rate for this time. Is this understandable?
Yes, sir.
Okay,
Yes, sir.
now
Yes,
see,
sir.
they are asking rate of reaction at 1 mole per dm cube. It means they are talking about at a specific point. For example, at this point, you have to find the rate. So what you will do, you will draw a tangent at this point. These rates are called instantaneous rates when you have to find the rate at specific point. So what we will do, we will draw a tangent at that specific point and then find the gradient of that tangent. That will be the rate at that specific point. That is the last thing that I need to discuss in this chapter. And here we are done with the whole rate of reaction. And in the next class, we will be starting with the ionic equilibria. Okay, if anyone of you have any confusion or any questions, please ask.
No, sir.
Okay, then. See you everyone in the next class. Take care, everyone. Allah
Okay,
Hafiz.
sir.
Allah
Allah
Hafiz.
Hafiz.
Allah